Z-score. The Z-score is the number of standard deviation a data value is away from the mean. So the Z-score of a value represents the distance or the deviation of that value from the mean in terms of a standard deviation. It defines the distance of a value from the mean in terms of a standard deviation. How many standard deviation a data point is away from the mean. To compute the Z-score of a data point, subtract the mean and divide the result by the standard deviation. The Z-score can also be used to define extreme outlier. A data value is considered an extreme outlier if its Z-score is less than -3 or greater than +3. If it's +3, then the data value is an extreme outlier on the right. If it's -3 or less than -3, then the data point is an extreme outlier on the left. The larger the absolute value of the Z-score, the further the data value is from the mean. Let's see the formula for a Z-score, the Z-score of a value. If you're talking about the Z-score of a data value from the sample, then we're going to use the mean and the standard deviation symbols from the sample, which is X bar and S. So Z-score of a data value from sample is X minus X bar divided by S. This is for sample. If you're talking about population, then the mean is shown by mu and a standard deviation is shown by sigma. So the Z-score of that value would be X minus that value minus mu divided by standard deviation, which is sigma. X here represents the data value that you want to find the Z-score for. X bar is the sample mean. S is the sample standard deviation. Mu is the population mean. And sigma is the population standard deviation. Locating extreme outliers using a Z-score. Let's see an example. Suppose we have a sample of SAT scores that the average is 490 and the standard deviation of the sample of SAT score is 100. So because it's a sample, we show the average by X bar, that's 490, and the standard deviation by 100, which we show it by S. We want to find the Z-score for a test score of a student that has got 620. So someone has got 620. We want to find the Z-score for that value. Z-score for 620 is 620 minus the average, which is 490, divided by the standard deviation, which is equal to 1.3. So what does this 1.3 means? It means the score of 620 is 1.3 standard deviation, which is 100, away from the mean, which is 490. And since the Z-score is less than +3 and greater than -3, it is not an extreme outlier. The Z-score of this test, the Z-score of the score of the student, the SAT score of the student, is not an extreme outlier. Let's work on a practice problem for finding Z-score. Suppose we have a set of data, a population data of 7 numbers. We have taken a small sample from this population, only 4 numbers. As you see in this table here, we want to find the Z-score of 14. So you need to find two z-score of 14, one that is in the population and one that is in the sample, because as you know, the standard deviation of population is going to be different. The formula is different also here because we have different numbers in the sample. They are in the population, but not all of the values in the population are in the sample. So we're going to have also different averages for these two sets, different standard deviation, different sample, different averages. So we're going to expect to have different z-scores. So please go ahead and pause and work on the problem. Find a z-score of 14 for the population and z-score of 14 for the sample, and then come back to see the solution. Okay, let's go ahead and find the z-score of 14 for population. So we need to find the average and the standard deviation of the population. The standard deviation is 5.095 and the average is 14.571. The z-score would be 14 minus the average divided by the standard deviation, which is negative 0.112. So this shows that it's a negative number that shows that 14 is below the average, which it is. 14 is below 4. It's less than 14.571. So now let's find the z-score of 14 for the sample. So we need to find the average and the standard deviation of the sample. The average of the sample is 14.75 and the standard deviation is 7.136. As you see here, both these values are different for the population and the sample. So we're going to expect to have a z-score which is different from the sample and population. So the z-score for the sample for 14 is negative 0.105, which is again less than, it's a negative, so it means that 14 is below the mean, which it is. 14 is below 14.75, so that's why we have a negative z-score. Okay. There are some interesting rules in statistics about the distribution of data that can sound really magical, especially the first time that you hear about them. One of them is called the empirical rule. The empirical rule applies to bell-shaped distribution data. So if your data approximately follow a bell-shaped distribution, something like this, it's called bell-shaped because you can actually imagine it is part of a bell like this. Right. So if the shape of your data distribution of your data is bell-shaped, the empirical rule applies. And it would say that approximately 68% of your data would fall within one standard deviation away from the mean. So as you see here, the distribution of the data is bell-shaped, the red plot here. So that's the only thing that you know. If it's bell-shaped, then approximately 68% of your data would be within this range. This is mu plus sigma, and the left one is mu minus sigma. So 68% of your data would fall between these two ranges. And that's very interesting. The empirical rule also says that 95% of your data would fall within two distribution away from the mean. So if you have a bell-shaped distribution, 95% of your data would fall between these two ranges, which is two standard deviation below and above the mean. And also 99.7% of your data would follow about 3 standard deviation above and below the mean. So if you have bell-shaped distribution, 99.7% of your data would fall between mu plus sigma and mu minus sigma. And these are really interesting and magical. We're going to see examples of these. Let's see an example of an application of the empirical rule to see how magical actually this rule can be. Suppose we have a group of students that have taken the SAT score, and we know that the distribution, the frequency distribution of the SAT score for these students are bell-shaped. And the average of these scores is 500 and the standard deviation is 90. That's all we know. You need to know. Then according to the empirical rule, 68% of all the students, their SAT scores would fall between 410 and 590. That is amazing. So without knowing any student's SAT score, you know that 68% of the group of students have a SAT score between 410 and 590. Also, 95% of students have a SAT score between 320 and 680. 99.7% of students, their SAT score is between 230 and 770. This is really amazing because you don't need to know any single student's SAT score. The only thing that you need to know is that you plot the distribution of the SAT score for this class, and you realize that, okay, it's approximately bell-shaped, and the average is 500, the standard deviation is 90. Then you can say 68% of SAT scores are between 410 and 590. 95% of students have a score between 320 and 680. 99.7% of students have a score between 230 and 770. That's really magical. Well, the empirical rule may sound interesting, but you might actually think, what if the shape of the distribution of my data was not bell-shaped? Well, we have another rule. It's called the Chebyshev rule. Chebyshev is actually the name of a Russian statistician who actually had immensely contributed to the science of statistics. According to this rule, regardless of the shape of the distribution of your data, whether it is bell-shaped or not, at least 1 minus 1 over k square percent of your data would fall within k standard deviation away from the mean, and k greater than 1. So you can have k equal to 2, k equal to 3, and etc. and etc. Let's see an example. We're going to go with k equal to 2 and k equal to 3. For k equal to 2, if you plug in k equal to 2 in this formula, 75%, at least 75% of our data would be 2 standard deviation away from the mean, regardless whether your distribution is bell-shaped or not. For k equal to 3, 89% of your data would be 3 standard deviation away from the mean. Again, it doesn't have to be bell-shaped or not. So this is the Chebyshev rule that can tell you about the distribution of your data, about the percentage, how much percentage of your data is between this value and that value, regardless of the distribution, the shape of the distribution of your data. And that's really magical. Also, you need to consider this. Don't forget that this is for the Chebyshev rule, we have at least 75%, at least 89% of our data would be between 2 and 3 standard deviation away from the mean. That's one difference from the empirical rule.